Okay, the last half of 5.5 is just combining our idea of U-substitution and definite integrals. So now we're just going to be finding the area underneath the curve from a to b, just like we were before, but in order to integrate, we might have to use our U-substitution idea from our previous videos. So look at example number 3a with me. It asks us to integrate the square root of 2x plus 1 from 0 to 4. So we want to find the area underneath the curve from 0 to 4. Or we want to find the antiderivative, the net change from 0 to 4. But if you were to rewrite this problem, to me this looks like a chain rule, right? If I have a 2x plus 1 to the 1/2, this looks like a chain rule. That's my clue that I'm going to use U-substitution in order to be able to integrate this problem. So I'm going to call U my 2x plus 1. That means the derivative is 2 dx. If you've noticed that there is no 2 in my problem in order to have my du, so I plugged in a 2 and I balanced it out with a 1/2. Remember, that's legal as long as you balance it out. So if I use my U substitution, I end up with a problem that says u to the 1/2 du. We're integrating it from 0 to 4, and then we have our 1/2 in the front still. Just like we did before, we can use our power rule. We can add 1 to our exponent, divide by that new exponent, and we're still evaluating it from 0 to 4. Now, we don't want to plug in our 0 and 4 yet, because our 0 and 4 were what we called our limits of integration with respect to x, and my problem right now isn't in terms of x yet. So I have to keep going all the way through the U substitution process if I'm going to keep the 0 and the 4 limits of integration. And so please don't plug in your 0 and your 4 yet. Make sure you finish your U substitution piece where you're plugging back in your u. And so you should have a 2x plus 1, that's what we called u in the first place, to the 3/2 power, all over 3. And now we can evaluate it from 0 to 4, since those are x limits and we can plug those in for x. So using our fundamental theorem of calculus, we can plug in our upper limit, our 4. We can plug in our lower limit, our 0. And then we can evaluate from there. So I have 2 times 4, which is 8, plus 1, which is 9. And then instead of writing it as 3/2 power, I'm going to do top dog goes in the house, and I'm going to put a square root of quantity cubed. I ended up with the square root of 9 cubed over 3 minus the square root of 1 cubed over 3. The square root of 9 is 3. 3 cubed is 27. 27 minus 1 is 26. I ended up getting 26 over 3. So combining my ideas of definite integrals and U substitution. Just being careful that you finish your U substitution process before you plug in those limits of integration if they're x limits. I'm going to do another example with you and talk about changing those limits of integration. So instead of using the 0 and the 4, maybe we can use something different. Let me show you an example number 3b. In example number 3b, you notice that we have an integral from 0 to 1, and to me this looks like a product rule and a chain rule, so that's my clue that we're going to be using U substitution again. And so maybe pause your video, see how far you can get with your U substitution piece, and then come back with me and we'll catch up with the integration and the limits idea. I'm going to call U my x squared plus 1. That means my du is 2x dx. And so if I were rewriting this, I have my u cubed, but in order to have my du, I need a 2x dx, and I have an x dx, I just don't have a 2, so I'm going to put a 2 in there as long as I balance it out with a 1/2. Rewriting my problem then, I have a 1/2 on the front, I have a u cubed, and then I have my du. But do you notice something? There's also a change in my limits. And they changed from 0 to 1, now from 1 to 2. And I got those new limits by, I'm calling them U limits, because what I've done here is when I had my 0 and 1 to begin with, those are in terms of x's. But now my problem is in terms of u's. So when x was 0, if I plug in a 0 here, what would u have been? Well, if x was 0, then u would have been 1, and that's how I got my 1 down there. And when x is 1, and I were to plug in 1 here, what would I have gotten? Well, then u would have been 2, and that's how I got my upper limit of 2. So I can change my limits from x limits to u limits by plugging in what my x limit was and turning them into u limits instead. So my 0 changed to a 1 and my 1 changed to a 2. And now let me show you what we do when we integrate this in terms of u's. So I'm going to keep those u limits. I'm going to integrate just like I would before using my power rule. So I have u to the 4th over 4. Don't forget you have a 1/2 in the front. And instead of changing my u back into the x squared plus 1, because I've changed so that I have u limits, well, now I can substitute in my 2 and my 1 in for u because those are u limits. And so I'm skipping all of the pieces here where I had to substitute in for x and then substitute in my x limits. You would get the same answer either way if you kept going and you kept your x limits, but it just kind of skips some steps for you. So using our fundamental theorem of calculus, I can plug in now my upper limit, I can plug in my lower limit, and then I can evaluate and get 15 over 8 as my area underneath my curve. That's just one option. That's just one way of doing it. Again, you could have kept the 0 and the 1, just back substituted this u in and called it back your x squared plus 1, and then substituted in your 0 and your 1, and you should have gotten the same answer. So whatever technique you'd like, just be careful not to combine the two. If you have x limits, make sure you plug back in your x expression. If you have u's, then you can use your u limits. Okay? So try a few ways, see which way you like best. Do you like the x limits and go all the way through, or you like to change them to u limits and then substitute in at your u step? Try it, see what you like, see what you feel more comfortable with. We're almost done. We're going to do one more video to finish off the semester, and then you don't have to listen to me anymore. Woohoo!